Welcome to EDU World Space.
24.60. So we have this situation where we're moving an electron from far, far away to be a distance of 8 centimeters away from some unknown charge q, and we're told that this takes a work of 2.16 times 10 to the negative 13 joules we have to do. So we want to find the charge on this ball, and then we imagine that the charge is split up into these 12 smaller charges, and then we move the electron to the middle of them, and they're all 8 centimeters away from the center here. And we want to find out what the change in potential energy is. So first, we know the work, and that has to be equal to the charge of our test particle times the change in the potential. So then negative E times Q over 4 pi epsilon naught R. This must be equal to that we're given, the 2.16 times 10 to the negative 13th joules. And so then just putting 8 centimeters in for R and the amount of work we have in solving for Q, we get that Q is equal to negative 1.2 times 10 to the negative 5th coulombs. Now in part B, we have the same net charge, and the electron is the same distance away from all of it. So here, delta U is the same as the work. Well, this is true in general, but it's also the same then as before, because in terms of the potential energy, moving it to a point where it's equidistant from charges that add up to the same charge as in this situation, the actual amount of work is the same. And if you like, you can work through it the long way to verify that. But this is also sort of a conceptually important thing, and so you should be able to recognize situations like this where there's something that could potentially greatly simplify what you have to do. And also, I mean, it's a deeper understanding of the physics than just like adding up the potential from each charge and then discovering you get the same answer and then, not really appreciating the significance of that.